In Chapter 3, we're going to discuss different ways to describe data. In particular, we're going to focus on numerical or quantitative data. This section of our course can be referred to as descriptive statistics. In the first section, we're going to talk about how to describe how data is centered. Then we'll talk about how data is spread. And finally, we'll look at comparing data by looking at measures of relative standing. In this first section, we're going to be introducing some terminology, including mean, median, mode, mid-range, and other measures of center. Our objective as we go through this section is not only to learn how to compute these different measures of center, but more importantly, how to interpret those values. First, we'll say that a measure of center is a value at the center or middle of a data set. And again, keep in mind we're talking about numerical or what we also refer to as quantitative data. We are not going to be able to talk about center when it comes to qualitative or categorical data, with one exception, and we'll get to that a little bit later on. When we talk about the mean in statistics, we're usually referring to the arithmetic mean. There is another type of mean called the geometric mean that has other applications, but for our purposes, we're going to talk about the arithmetic mean, which is what most people refer to as an average, loosely speaking. In statistics, we're going to avoid that term, the term average, as it is vague and can be misleading, so we are going to refer to the arithmetic mean as the mean. And what it is the measure of center that we find by adding all of the data values in our data set and then dividing that sum by the total number of values in our data set. As I said earlier, we're going to avoid using the word average, even though most people would use that term in place of mean. It is not something we use as statisticians, and again, in our community, it could be vague and misleading. Let's talk about some of the properties of a mean. First of all, when we draw samples from a population of interest and calculate the means of those samples, we find that those means tend to be pretty close to one another. They vary not so much from one sample to the other. And so we say it's a pretty reliable way of talking about the center of a population if we were to draw multiple samples and look at what's happening in the means of those samples. The mean of a data set does use every single value in the data set, and that does come with a catch. If we have a data set that has any outliers, values that are far removed from the others, those outliers could have quite an impact on that calculation. And because the mean is easily influenced by those extreme values, we say that it is not resistant. Resistant, of course, in English means kind of not easy to sway, kind of holds its ground, very consistent, not easily changed. And because the mean is easily affected by extreme values, it is not resistant. So the word resistant in statistics means that in the presence of extreme values, either very small values in comparison to the rest or very large values in comparison to the rest, that a measure is resistant if it does not change very easily in the presence of such outliers. The formula to calculate the mean is known to all of us. Here it is in its most concise representation using some mathematical notation. First of all, you see this E-looking symbol. This is actually the capital Greek letter sigma, and in mathematics we use that symbol to denote a sum or addition. So having that uppercase sigma next to the letter x tells us that we're adding up these x values. We're looking at the sum of those values. and the lowercase letter n in the denominator refers to the number of data values in our sample. So basically, if we add all of the values and then divide it by the total number of values, we compute the mean. Now we're going to look at some different notation depending on whether we're looking at a sample or we are looking at data that comes from the entire population of interest. So we're going to look at this symbol that has the X with a little bar on top, and it's actually pronounced X bar. That's going to be our notation when we're computing a mean from a sample. And then we're going to be using a different symbol right here. It kind of looks like a curly M. It is the Greek letter mu, and that is what we're going to use to denote a mean that is calculated from values coming from the entire population. This way we can keep track of whether the mean is representing a sample from the population, which is a subset, or whether that mean is representing the entire population of interest, just by looking at which letters we're using. So again, that sigma symbol denotes a sum or addition. X is going to stand for the data values themselves. So X is the variable that is taking on all the data values in the data set. Lowercase n is going to represent the number of values in a sample. Uppercase n is going to denote the number of data values in the entire population. So here we see the mean computed. It's basically the same formula. The one above is using lowercase n for the sample size, and therefore it is the sample mean, which is denoted with the X and the bar on top, X bar, whereas the formula down here looks the same, but we have a capital N in the denominator. That means that we have the population size as our what we have in the denominator, and because we're talking about values from the entire population of interest, we are going to say that this is the population mean, which we denote with the Greek letter mu. In this example, we have some values that represent the wait times at Disney World, let's say for a particular ride. It says here for 6 popular rides. So we have the values 50 minutes, 25 minutes, 75 minutes, etc. And we're going to look at how to compute the mean of this data set. The process is very straightforward. We add the wait times, and then we divide that sum by the total number of values in the set. So if we were to count how many wait times we have here, we would see that there's 11 wait times. And so we find that the mean wait time is 39.1 minutes. And they're saying here this is for Space Mountain. The median, on the other hand, is a different measure of center, and it denotes the middle value in a sorted list. So we have data values that are sorted from least to greatest, or from greatest to least, it doesn't matter. But basically it's the middle value in a sorted list. One of the properties of the median is that it is not easily influenced by extreme values, not easily influenced by outliers. Why? Because it's hovering in the middle. So if we were to add a really small value in comparison to the rest, or were to add a really large value in comparison to the rest, really the middle is not shifting very much. So we say that the median is a resistant measure of center. It is not easily influenced by large or small values. Now, the median does not use every data value. In fact, it's going to be either the one single value directly in the middle, or if we have an even number of values in our list, it's going to be the mean of the 2 middle values that are kind of competing for that middle spot. So that's one of the reasons that the median is not easily influenced by outliers. The median has a few different symbols. One that we see in computer output sometimes is X with a little curly symbol on top. That is pronounced X tilde. More commonly though, we either see the capital letter M or the letters MED to denote the median. The process for finding the median is very straightforward. First, you need to have a sorted list, so it has to be arranged in either ascending or descending order. If you have an odd number of values, there will be a clear middle value. If that's the case, that's the median. If you have an even number of values, then there's going to be two contenders kind of fighting for that middle spot. In that case, you're going to add those two middle values together and divide by 2, essentially finding the mean of the two middle values, and that will be your median. In this particular example, we have the 11 wait times that we saw before, and this time we're going to compute the median. First, we're going to sort the values. In this case, they are in ascending order. The lowest value 20 is on the left, the highest value 75 is on the right. Because 11 is an odd number, there is a clear middle value, and that is the number 35. That is the median for this set. Now we have a 12th value that we're kind of throwing into the mix. So this list has the 11 values that we saw previously plus a 12th value. So if we were to sort these 12 values to find the median, we would have to take the mean of the middle two values that are kind of fighting for that middle spot. So in this case, the two middle values are right here. 35 and 45 are the two middle values kind of competing for that middle spot. And so to find the median, we will add those two values and divide by 2. And in this case, the median is 40 minutes. The mode is another measure of center. The mode is whatever value occurs the most in your data set, the value that has the greatest frequency. Sometimes we have one mode, so one value occurs more than all the others, and sometimes we can have multiple modes or no modes at all. You might recall earlier I said that we're only going to be talking about measures of center for numerical or quantitative data, with one exception, and this is the exception. The mode is the only measure of center that can be used for categorical or qualitative data. For example, if we were talking about favorite colors, and the choices were blue, red, yellow, and green, we clearly could say that one of those colors was the winner, the one that had the most favorite votes, because it had the highest frequency. So whatever category had the largest count or the largest frequency would be the mode, and that would be the only measure of center that we could use for categorical or qualitative data. To find the mode, you will just have to see what the frequency is for each one of the values in your data set. Again, there could be one clear mode, one value that occurs more often than all the rest. You could have more than one mode or no mode at all. When there are two modes, we say that the distribution is bimodal. When there are more than two modes, we say it's multimodal. And again, if there is no data value that is repeated, or you do have repetitions, but all the data values are repeated with the same frequency, then we would say that there is no mode. In this example, we have our 11 wait times. These values are a little different. It says here that we're looking at a different Disney ride, the Tower of Terror. And so we have 11 values in our list, and we want to see if we have a mode or no mode or multiple modes. So we see here that after sorting the list from least to greatest, the value 30 occurs twice, the value 35 occurs 3 times, and the value 50 occurs twice. So the mode here is 35 because it is repeated 3 times, so the frequency here is 3. The frequency for all other values is less than 3, and so 35 would be our one mode. Let's look at another example. If our data set was a little smaller, let's say that we only had the 5 values 30, 30, 50, 50, and 75. Then the value 30 has a frequency of 2, the value 50 has a frequency of 2, the value 75 only has a frequency of 1. So because 30 and 50 have a higher frequency and they have the same frequency as the other, we say that both 30 and 50 are modes. This is a bimodal data set. It's a very small one. It's just for the purposes of demonstrating the process, but it does have two modes. And if we had the following 5 data values in our set, 20, 30, 35, 50, and 75, notice that none of the values are repeated, and therefore there is no mode. And I want to remind you that if they were all repeated but with the same frequency, we still would have no mode. For example, if the number 20 was repeated 3 times, and the number 30 was also repeated 3 times, 35 was repeated 3 times, 50 was repeated 3 times, and 75 was repeated 3 times. Even though we have repetitions, the frequencies are the same, there's no winner, and there would be no mode. Another measure of center is the mid-range. The mid-range is not readily used in statistics because it is very easily influenced by extreme values, as you'll see in a moment. However, we talk about the mid-range because it is often confused with median. The mid-range is very easy to compute. It is simply the smallest value in your data set added to the largest value in your data set and then divided by 2. So essentially it's the mean of the minimum value and the maximum value. Now, it is very easy to calculate, but you can imagine that if you're grabbing the smallest value in the data set and the largest, if there are any outliers present, you're catching them. And therefore, the mid-range is going to be very easily influenced by those extreme values. So it's not resistant. It's not one of the values that statisticians use with any validity. However, it's easy to compute, and again, we like to talk about it here because sometimes students confuse the mid-range with the median, and if nothing else, it's a non-example of what a median is. Some redeeming values of the mid-range, however, like I said earlier, it's easy to compute. It points out that there are different ways for us to talk about the center of a data set, and again, it makes it clear that this is not the same as the median. The mid-range for this data set, the minimum value is 20, the maximum value is 75. We add those two together and divide by 2. In this case, we find that the mid-range is 47.5 minutes. Whenever we're calculating measures of center, we want to make sure that we increase the accuracy or the precision of our calculations. So whenever we're calculating the mean, the median, or the mid-range, we want to go out with our calculation at least one more decimal place than the original data did. So if we had, let's say, whole numbers for our original data, we would want to take these calculations out to 1 decimal place. If the original data had values out to 2 decimal places, we would want our mean, median, mid-range calculations to go out at least 3 decimal places, and so on. So we're always adding 1 more decimal place to the calculations so that we have a little bit more accuracy. We can always calculate the measures of center from a sample of numbers, but in the back of our minds, we should always be thinking about whether it makes sense to even compute those values. We're going to see some examples where it would not make sense to compute the mean. Additionally, if we're looking at examining samples from a population in hopes that we could draw some conclusions about the population where the samples were drawn from, we want to think about how the sampling method may have affected these values. In this example, if we were to have a list of zip codes, it wouldn't make sense to find the mean of the zip codes because zip codes, after all, are not numerical data. Those are numbers that serve as labels. So this is categorical, and therefore it would not make sense for us to compute a mean zip code. ranks of selected medical schools, the top school, the second school, the third school, etc. If we're using a ranking, again, this is not numerical data. This is what we refer to as ordinal data, and therefore we would not use the mean as a calculation. Numbers on jerseys, same as before. These are not numbers that are actually serving as numbers. They're serving as labels. So it would not make sense to compute measures of center such as mean or median. In this case, we want to make sure that when we're computing mean and median, that we're looking at values that are numerical in the sense that they are measuring or counting. And in this last example, we have the salaries of some CEOs. This is numerical. In fact, it's the ratio level of measurement. So we certainly could find the mean salary. However, in this example, it's telling us, if we're looking at the top CEOs, this is not representative of all CEOs. We're only looking at the top 5, and so our sample is not representative of the population that we might want to make a statement about. The 50 mean ages computed from the means of each of the 50 states. Well, on the surface, this may seem okay. Why not take the mean of the means? The problem here is that, as you saw earlier, the mean is computed based on the total number of values. We have 50 states, however, they have different populations. And so if we were to take the mean of, say, the age of people in Florida versus the ages of people in North Dakota, the people in North Dakota would have a larger voice in that mean calculation because they have a much smaller population than Florida does. So whenever we have different denominators, we have different population sizes or different sample sizes, and we want to look at the mean of means, we usually turn to what is referred to as a weighted mean. We're going to talk about weighted means in just a moment. First, we're going to look at how to compute the mean from a frequency distribution because this is going to feed into our discussion about weighted means. So if we have a frequency distribution, and we talked about this in chapter 2, we have one list that has our values typically either completely listed out separately or grouped together into classes. And then we have a second list, a second column, for instance, that would have the frequency for each one of those values or each one of those classes. To compute a mean from a frequency distribution, we need to multiply each original data value by its frequency and then add those up. Then we're going to add up all of the frequencies because that is going to give us the total number of values in our set, and that is what we divide by. This formula may seem a little intimidating, but as we go through an example, you'll see that it makes perfect sense. In this frequency distribution, for instance, and we saw this one several times in chapter 2, we have a frequency distribution with grouped data. So we have a class that includes times from 0 seconds to 14 seconds and so on. That means that we do not have the original data values in this table, and to compute the mean, we're going to be doing some estimating. Because we don't have the original data, what we're going to use instead is the midpoint for each one of these classes. Remember that the midpoint for a class is found by adding its lower class limit to its upper class limit and then dividing by 2. So in this case, 0 plus 14 is 14, and then divide 14 by 2 and we get a class midpoint of 7. So we're going to pretend that the 6 values that are in this first class are estimated by having a value of 7. Again, this is an estimate because In this first class, we could have values like 1 and 3 and 11 and so on. We don't know what the original values are, so we're just going to say that 7 is a good estimate for what the values are in this class, and that there are 7 such values. And we're going to do that for each class. So the midpoint for the second class is 22, the midpoint for the third class is 37, and so on. Once you find the midpoint, you multiply it by the frequency for that class, and that's what we get here in this last column. So for instance, this 335 was found by multiplying the frequency of 5 by the class midpoint of 67, and that's how we end up with the 335. Then we're going to add these products, and we get a sum of 1,730. That's going to be the numerator of our calculation. If we add up the frequencies right here, we get that the sum of the frequencies is 50. 50 is how many original data values we had. So dividing the 1,730 by 50 gives us our estimate for the mean of this distribution, which is 34.6 minutes. Again, this is an approximation because we're not using the original data values. We are using the estimates of those data values by having those class midpoints take the place of what the original data values would have been. Now, when we're calculating a weighted mean, certain contributors have more importance or a heavier weight than others. We see this when we deal with grades all the time. If you have a course where you have homework assignments and maybe some discussions, maybe there's an attendance grade, you have tests, maybe you have a final exam, you certainly wouldn't compute your course average by adding your attendance grade to your final exam and then dividing by 2, because your final exam is going to carry much more weight than your attendance grade, for instance. So each one of those categories may be weighted differently. In this formula, we have what those values are, represented by X, and then W is going to be representing the weight. And we can have W as a percentage or as a decimal, representing what portion of that final calculation is going to be attributed to each one of these values. And then we're going to add up those products in the numerator. In the denominator, we just take the sum of the weights. And finally, we get the mean. Again, the formula might seem a little bit more intimidating than it needs to be, and we'll go through an example to help you see how to use the weighted mean formula. In this example, we have a college course, 5 college courses taken by one student. The final grades for this student are given, and the 5 courses had different credits associated with them. So, for example, this student was able to earn an A in a 3 credit hour course, another A in a 4 credit hour course, a grade of B in a 3 credit hour course, a grade of C in another 3 credit hour course, and unfortunately earned an F in a 1 credit course. Well, thank goodness, that was the one with the smallest weight. If we assign a grade of A as being equal to 4 points, a grade of B as being equal to 3 points, etc., we can compute this student's grade point average for that semester using our weighted mean formula. So our weights in this case correspond to the number of credit hours. Remember that the A came from a 3 credit hour course, the second A came from a 4 credit hour course, etc. So we're going to multiply each letter grade by the corresponding number of credits. So that 3 credit hour course multiplied by the 4 points that came from the A, plus the 4 credit hour course multiplied by the 4 points that also came from a letter grade of A, We had a 3 credit hour course where there was a B earned, so that 3 represents B. Another 3 credit hour course where there was a C earned, so the C is given 2 points. And then we had the 1 credit hour course where the student earned an F, and an F has 0 points. And so we have all those products, and then we're going to add those products together. The numerator becomes a 43. And in the denominator, we're going to add the number of credit hours. This student took 14 credit hours, and so her GPA for the first semester is a 3.07. So in this case, remember that our original data values were whole numbers, right? And A was represented by a 4, 3 was represented by a 3, and so on. So if we use the rule we talked about earlier, where we go out 1 more decimal place in the original data, we really only have to go out 1 decimal place here. So we would round the mean to be a 3.1.